Hi, in this video we are going to study the extrinsic semiconductors. In previous video we have learned what are intrinsic semiconductors and how do they conduct electricity. Now, extrinsic semiconductors are formed from intrinsic semiconductors. We know that intrinsic semiconductors are the pure crystals of semiconductor elements. We have two semiconductor elements, silicon and germanium. In previous video we had taken the example of silicon. Now also we are going to take the example of silicon only. We can do these things with germanium also, but here we are going to take example of silicon crystal. Now we know that if we have the intrinsic semiconductor of silicon, that means we have pure crystal solid of silicon. That means in the crystal all atoms are of silicon, and we know silicon has 4 valence electrons. But now if I replace some of the atoms of that solid crystal with some another atom which does not have valence electrons 4, it can either have 5 valence electrons or 3 valence electrons. Then that atom which replaces the silicon atom from its pure crystal will be known as impurity, and the addition will be very small. It will be near about 1:10 to the power 6. For that pure crystal, the impurity will be very less. Now, what happens? We know that silicon has 4 valence electrons, but when solid is formed, there is sharing of electrons and they complete their 8 electrons. But if now I add an atom with 5 valence electrons, there will be same sharing of electrons and there will be complete 8 electrons in the orbit. But there will be 1 valence electron. How? Let us see this. This is 2 array diagram of a crystal of semiconductor silicon, but 1 atom is replaced with an impurity. This is pentavalent impurity. That means it has penta. That means 5 valence electrons in it. Now what happens? Electrons have to be in some bond. Now 4 electrons of this also forms the bond as silicon made in intrinsic semiconductors. But we have seen that it has 5 valence electrons. That means 1 electron is not going to take place in any of the bond. So that means this is free to move. This valence electron has no bond in this crystal. So, if we see the conduction band and valence band diagram of this semiconductor in which we have added impurity of 5 valence electrons, we will see that all the electrons of this crystal which are bonded to atoms through this covalent bond, they are present in this valence band only. They have energies of this band only. But this electron which is free, which is not in any of the bond, it has energy greater than these electrons which are included in bond. Why? Because we know that if this electron is free, that it is free but it is bound to its nucleus only. What is happening to this electron? This electron has only the attractive power of its nucleus. So it has that much of energy in it. But if we talk about these electrons which are in bond, what is happening to these electrons? These electrons are under the influence of this atom also as well as this atom also. That means these electrons are under the influence of 2 atoms in which they are forming the bond. That means these electrons will have less energy. It is free. That means it has more energy. So the valence band and conduction band will have another energy level in between them. This energy level have those electrons which are not taking part in any of the bond. So this level, energy level, is called donor energy level or Fermi level of the extrinsic semiconductor with pentavalent impurity. Now we can see that this semiconductor has an impurity which has donated an extra electron to the semiconductor in comparison to the intrinsic structure of this semiconductor. So that means this atom is donor atom. that means this atom is called donor type atom. And those semiconductors which are formed by donor atoms are called N-type extrinsic semiconductors. Now if I talk about the impurity of trivalent, that means it has 3 electrons, valence electrons. That means this type of structure will be formed. Now we see that silicon atoms has 4 electrons and it shares 4 electrons from the neighboring atoms to complete its shell. But if a trivalent impurity is introduced here, these silicon atoms will fulfill their demand by sharing. But this silicon atom has no electron for sharing with this. So what it means that this place for the bond is empty. So that means a hole is here. So actually this atom which is introduced as impurity has tendency to attract electron from the other atom. So that means this atom has a capacity to accept the electron from other atom. So this type of impurity which has trivalent electrons is called accepting atom or an acceptor. So these type of semiconductors which are formed by replacing the atom in intrinsic semiconductor with an atom with 3 valence electrons is called P-type extrinsic semiconductor. So we got to know that extrinsic semiconductors are the semiconductors which are formed from intrinsic semiconductors only, but they can be formed in 2 ways. Either by adding an impurity with 1 more electron or with 1 less electron. If we add the atom with 1 more electron, that is pentavalent impurity, the extrinsic semiconductor formed will be N-type extrinsic semiconductor, and if we add an atom with 3 valence electrons, the semiconductor formed will be P-type semiconductor. So these are the 2 types of extrinsic semiconductors, and the process of adding impurity to this crystal is known as doping. Now, if we watch the conduction band and valence band of P-type semiconductors, that is the semiconductor formed by adding impurity of 3 valence electrons, we will see that the energy level is formed here just above the valence band. This is the level of holes, and this Fermi level is called acceptor energy level. Now, if we talk about conductivity in extrinsic semiconductors, we will talk about conductivity of N-type and P-type differently. First of all, we will talk about the conductivity of N-type semiconductors. For N-type semiconductors, we have pentavalent impurity and there is this kind of energy level. Now, as we know and we have discussed in the previous video that in semiconductors the current is produced because of the flow of holes as well as electrons. So we have to see that how free electrons and holes are present in N-type semiconductor. So, first of all, the electrons which are different from intrinsic semiconductors, these electrons of pentavalent which are different, the electrons which are not in any of the bond are present at this energy level. Now at absolute temperature, no movement is there. But if we talk about room temperature, what happens? We increase the temperature, this electron has very less energy gap. They will suddenly jump to the conduction band and will become free electrons and will contribute toward the current. So we get free electrons as soon as room temperature. That means extrinsic semiconductors are better conductors than intrinsic semiconductors, because even at the minimal temperature they have free electrons and they start conducting, whereas in intrinsic semiconductor this was not the level present and the electrons have to jump from here. Now when at room temperature this free electron jumps to the conduction band and moves towards the current. Now these electrons are also present in this semiconductor as in intrinsic semiconductor. So what happens here? The same case as was done in intrinsic semiconductor. What happens at room temperature? There is thermal agitation in this crystal. So electrons start moving fastly. What they do? They break their covalent bond. They shift from their place, and suppose this electron gained the energy and shifted. What it will do? It will gain energy and will jump to conduction band. So we will get a free electron here also. And correspondingly a hole is generated. So one thing we have to take in mind that in intrinsic semiconductor, if we had one free electron, we had one hole. But here we can see that we have two free electrons but one hole. That means in extrinsic semiconductors, number of electrons, extrinsic semiconductors of n type, number of electrons is more than number of holes. But one thing strikes in our mind that if the number of electrons are more, that means negative charge is more on the semiconductor. That means extrinsic semiconductor of n type should have negative charge on them. But actually it is not so. Why? Let us see. If we talk about electrons and the atom. Now atom is there. It has nucleus and electrons are around it. So this is the nucleus of silicon atom and it has 4 valence electrons. These are the 4 valence electrons. Now this atom as a whole had 14 atomic number silicon, 284 configuration, 4 valence electrons. So this atom as a whole is neutral because its nucleus, if we talk about valence electrons only, because we are representing valence electrons, 4 valence electrons have 4 protons in the nucleus. That means it is electrically neutral. Similarly here and all other silicon atoms. That means we say that silicon atoms are not contributing towards the charge. Now if we talk about this impurity, it is a pentavalent impurity. We say that it has 1 electron more. That means it is giving some negative charge. But actually it is not so. Why? Let us see. Now this atom is pentavalent. That means it has 5 valence electrons. Now it is an atom. We know that the number of electrons around the nucleus in an atom is equals to the number of protons in the nucleus of the atom. So that means if this atom has 5 valence electrons, that means it has 5 protons in its nucleus. That means this is also electrically neutral. So all in all, though we have number of electrons more, but we have number of protons also increased in the semiconductor. So this extrinsic semiconductor, n-type semiconductor, is also neutral. So one thing we have to keep in mind is that the semiconductor has number of electrons more. This n-type semiconductor has number of electrons more than the number of holes, but still it is electrically neutral because of the core of this atom, that is the nucleus of the atom. Because we haven't, the semiconductor will have electric charge or negative charge on it. If I have a crystal and I introduce an electron in it, it will get charge, negative charge of an electron. But I have replaced an atom from it. That means I have replaced the nucleus as well as the electrons. Now if I have replaced an atom, the atom is neutral. So I have introduced a neutral thing in the crystal. So why it will get charge? So the extrinsic semiconductor is also neutral. So we have representation of n-type semiconductors. Now representation of n-type semiconductors is like this. N-type semiconductors have difference in what? They have a pentavalent impurity. Silicon atom have 4 valence electrons, that means 4 protons in its nucleus. But pentavalent electron is added in it. So in representation we will only show the pentavalent atom. In pentavalent atom means 5 protons in the nucleus of the atom with 5 valence electrons in it. But how they differ from the silicon atom? Silicon atom have 4 protons in its nucleus and 4 valence electrons. If I have introduced a pentavalent impurity, let it be arsenic. So it has 5 protons in its nucleus and 5 valence electrons. So how do they both differ? In representation we will show that this is a semiconductor of silicon, but it has impurity in it, and that impurity is donor atom, that is, this is n-type semiconductor. For this I will represent it like this. Why I have represented it like this is that this impurity differs from silicon. How it differs? That it has one more proton in it. So plus 4 for silicon and plus 1 for arsenic. So plus is represented here. And it has one extra electron. So one extra electron is shown. So this is the representation of n-type semiconductors. So this is the main thing for p-n junction also. So this is the representation of extrinsic n-type semiconductors. Now, if I talk about p-type semiconductors, for p-type semiconductors we have atom which has 3 valence electrons. Silicon has 4 valence electrons and 4 protons in its nucleus. I am just talking about the valence one. Now if I introduce some impurity in it which has 3 valence electrons, let it be indium, so it will be plus 3 and 3 of its electrons. This is the thing. So for representation of p-type extrinsic semiconductor, what we have? Indium is different from the silicon by -1. That means if I subtract 1 proton and 1 electron from silicon, I will get indium. So representation of this is the donor atom which have 1 proton lesser than the silicon. So I have used -1, that is, if I reduce my -1 from silicon, I'll get this proton. Now if I have 3 valence electrons, that means I have a empty space in my crystal that is represented by a hole. So I will represent a hole here. So this is the representation of p-type extrinsic semiconductors, the negative with holes. This representation is very important for the p-n junction, which we will discuss in later video. So these are the p-type and n-type semiconductors, and we have shown you that in n-type number of electrons is greater than number of holes, and for p-type number of holes will be greater than number of electrons in similar way when we will see the diagram. So this is n-type and this is p-type, and both are electrically neutral, though this is there, but they are electrically neutral because of the nucleus of the impurity added. And in both of them the current will be more in comparison to the intrinsic semiconductors, because in intrinsic semiconductors we have holes and electrons formed just because of thermal agitation. But in these, if we talk about n-type, we have electrons more than that produced by the thermal agitation, because we have free electron of that impurity. and here we have hole as charge carrier more, because the vacancy is always created when an impurity is added. So the current produced by an extrinsic semiconductor is always more than intrinsic semiconductors. That is why these were formed, because at normal conditions or for practical use, intrinsic semiconductors gave very low amount of the current. So this is basic concept of extrinsic semiconductor.